fine. So this is working. Thanks. Yeah, excellent. Oh, yeah. Okay. Is this the right time? Or do you know? I'm just wondering. I'm just wondering what the time exactly is. Mine is 15 past, but you are okay. 30. This is something like that. Okay. Okay, we will start. Yes. Okay. Okay. So then we. Okay. So I think we will just start now, and today I will talk about methods for evaluating glacier surface mass balance. Others, Anil Kulkarni is also talking about that, but anyway, I'm going to say something about it, and you will. And then I will just remind you from the earlier lectures that we are dealing with a glacier which I'm drawing up a cross-section of, like that. And we have been talking earlier about that in the upper part above the Fern line, snow is continuously accumulated and changed into ice. And then it starts to flow due to its own weight, due to gravity, down like that. And it emerges then as ice here in the ablation area. And you know already that the mass balance of this glacier is positive here because we have a gain in mass here. But in the ablation area, we are losing mass every year. So the mass balance there is negative. and the flow of the glacier is compensating for the loss here in the ablation area. So ice is continuously transported down into the ablation area up to the surface of the glacier here. And then in the end, the runoff is flowing from the glacier. But then, so we are faced with this situation that in the end of the winter, the glacier may look like something like that. And the question is how much mass has been added to the glacier during the winter. And then at the end of the summer, and now I'm talking about what I'm used to, one accumulation season, so it's just a winter time when snow is accumulated on the glacier. And then we have the summer when the glacier is losing mass. But there are two accumulation seasons somewhere here in the Himalayas. So it's, but let's just keep it simple. So we have the accumulation, and I've earlier shown this. It's any addition of snow to the ice. It can be snowfall. There's a lot of snow here. It can be drifted by wind from the neighboring mountain peaks and collected here on the glacier. And we can have avalanches from the mountain slopes down to the glacier. And furthermore, we can have water, freezing or rain falling onto the glacier, and freezing because the glacier temperature is below freezing point. And we can also have some melting on the surface, but then the meltwater percolates into the glacier and into cold snow and freezes again. And we call that internal accumulation. It's inside the glacier, and we are not because it is adding to the. So anyway, water or meltwater, which may look like disappearing into the glacier, may not disappear at all, but freeze again, and we call that internal accumulation. And then we have the ablation, which is any removal of snow. It can be meltwater, or melt just after it's melting and draining away. It's mainly on the surface, but there may be some meltwater produced at the base of a glacier if it is warm-based. And then we have wind erosion, which is just the opposite to wind-drifted snow. It may be blowing off the glacier. But then we have calving. If the glacier is terminating in the water, in a lake, ice may be broken off. Well, it's of course the main ablation process in Antarctica, where there is almost no melting. There is some wind erosion or blowing out to the ocean from the internal parts of Antarctica. But calving, breaking off into the ocean is the main ablation process. And finally, we can have sublimation, and which is common in tropical glaciers. And then the air is so dry that the ice, the molecules simply go from solid state straight into vapor without melting. So that is sublimation. But it's not so common on glaciers in general, except You can have that during very dry periods and when the and really cold weather. It is. We will have a small exercise illustrating this maybe tomorrow. And we have now I'm repeating. So we are faced with how do we measure this? You remember that I was showing this graph. We were going through the changes in this cross-section from one spring, for one glaciological year, from the spring. So we have this surface in the springtime, and so we have been adding snow on top of the glacier here during the winter. Then we have the next summer, fall, and everything is disappearing here until we are down to no, this is something. Well, what I was, I'm a little bit confused about this graph now. But anyway, we have accumulation during the winter time. We have to measure that. And we have ablation during the summertime. Something is left in the upper part here at the end of the summer, but here in the lower part there's a reduction. And the question is, how do we measure it? And there are two approaches. And one is which I would call in situ. There are often you see the glaciological method. I find that not a good term, but it is in situ. This is Latin and means that you do it on the place. You go to the glacier and you do something, you measure something there. But you can also, and I'm writing here ex situ, which is you are not on the place, you are looking at this from distance. You can do it by remote sensing or whatever technique, but you are not going to the glacier itself. And so I like these terms. And now we start to look at this in situ method. You go to the glacier and you do some measurements. And now we just look at what we do in a single point. You go to the glacier, you are in the late winter before melting starts, and you put a stake and you call it an ablation stake. It's a long road just like this, and you put it into the glacier, and then you have this amount of snow. The stick is a little bit above the snow level. It's like this. So this is the glacier, and okay. So it's HW centimeters or meters above, and then you have a snow thickness of that, and further down you are into ice, because when you come deeper down the snow is changing into ice. But anyway, you measure this, how much snow you have, and I will tell you later. You dig pits or drill into the snow to find it. And what you do is that you measure the thickness and the density. So there are two parameters you need to know to do the job. You come back in the late summer after the ablation season. In the accumulation area, you have lost this amount of snow, but there's some left, because you're not melting everything. And you measure the thickness of what is left of, this is the original thickness. So this is left, and you measure the thickness, the density of that, and it will have increased the density during the summer, because the processes I described, which we sometimes call metamorphism. But anyway, the snow is changing with time, and therefore the density is increasing. So that was the job in the accumulation area. If you go to a point which is in the ablation area, the situation is different. You lose all the snow which was accumulated there during the summer. And not only that, you will melt old ice in addition to that. So this is the situation that this ablation stake is now sticking above the glacier surface, a length equal to HS, which is so this is, and okay, so you have lost all this, and in addition some ice. Well, you would assume that the ice density is about 0.9 or 900 kilograms. So that is one of the assumptions. We are not bothering about measuring the density of the ice. We are only dealing with we assume that it is close to pure, the value of pure ice. So this is how you go about, you drill with a shovel into a pit into this, and this is a hard job. You can also have a drill, and this is a quarter, so you are drilling, putting it down in here, and rotating it and drilling, and you get a sample of the snow in the drill, and you take up the drill and take the snow core out of the drill, and you put it into small pieces, and you weigh it. You find out how much there is in a container of 1 liter or a given volume. So this is so you do density measurements in snow pits, and you do coring, and then. Here we have some colleagues. One is visiting us from Denmark. The first thing you do is you convert the snow thickness into water. It's convenient to just work to have any measurements in a thickness of water equivalent. So you take the snow thickness you are measuring, it has a density which you measure, and you divide that by the density of pure water. So then you are scaling all your measurements. So when you are saying how much there is of snow, you say it's 1 meter. It's equal to 1 meter of water. That might be 1.5 meters of snow, but you. So the thickness of the snow doesn't tell you much about the mass, and you can draw up figures like that. You are measuring this step by step down into the hole, into a snow pit. I mean. And you can draw up an accumulated curve for this, and this is just data processing, which I'm not. So okay, so now we are still looking at mass balance in a point, and we call that specific mass balance. Specific is a term used by glaciologists about a value in a single point. And we agree that we should give up the numbers in meters of water, or we can say this is kilograms per square meter. But anyway, this is a value of how much water equivalent there is. And in the spring, we derive the winter balance. It's not only a value, we call it the winter balance rate, winter balance rate. That's how many meters of water per year. And then we are over to balance rate. Meters is just the balance, but how many meters per year is what we are also asking for. And then we call it the winter balance rate. Sometimes we don't bother to say rate, but you can see from the units what you are talking about. So what we are talking about is that in this point we had an accumulation rate during the winter, which was C, and an ablation during the winter. It might be melting during the winter, which is this. So what you are measuring indeed in this point is indeed the net balance in that point during the winter. Because if you want to know the winter accumulation and the winter balance, you would have to stay on the glacier for the whole year and observe it. So we have to accept that what we get out of our measurements in the springtime is indeed the balance over the winter. There might have been some melting there, but anyway, we don't know. And next fall we go to the same point again, and then we obtain the summer balance rate. There might have been some accumulation during the summer, might be some snowfall during the summer, but there is a lot of ablation during the summer. So we admit that the only thing we get out of by visiting the glacier in the fall, in the spring, and again in the fall, is the balance over the summer and over the winter. So that is what we get. And then we can say, now we have been, the annual net balance would be the winter balance plus the summer balance. That would be the net balance. This is, I'm writing plus here, but of course this is negative in most cases. So this is what we have in a single point. and we can do this in many, many points all over the glacier, and then take the integral or over the surface. I didn't find the integral sign, so I'm just writing the sum here. And in that case, you are over to, this is meter per year, but if you integrate over an area, you will get the volume. And then we use capital letters. So it's cubic, so it's meters per year, or often it is a million of liters. So. But anyway, that is And you can integrate this over the accumulation area or the ablation area over the entire glacier. It's up to you what you are interested in. And I can show you some examples. There is a glacier in Sweden called Glacier, and since the 1940s, they have measured this glacier in large details. And here you can see the boundary of the glacier here. The mass balance in several hundred points, if I can. And they are doing this at 100 meters spacing. It's unbelievable. They don't do it by digging 100 snow pits, but they have poles like that, and they put them down into the snow until they feel that they are at the last year's summer surface. This is an art, but anyway, they have experience in this, because when you come through the winter snow and hit the old snow, it's harder. But this is, well, it's a problem if you have melting during the summer and ice lands produced in the winter snow layer, then this is very, very difficult. But this has been possible in northern Sweden. And they can see that the snow depth here is highly variable. So they prefer to do many hundred pounds. But the snow density is not so variable, so they take only snow densities in a few places just and use and extrapolate from few measurements over the glacier when they are estimating the density. So this is the result. They have a map of the very detailed map of the winter balance, and it's on for a year 1999, and it is yes, 1.36 meters water equivalent. So we write to be quite sure that this is not snow thickness, but this is water. Then we write water equivalent. 1.36. The summer they lost 1.4. So the loss is higher than the gain, and the net balance is minus 0.1. And here we have the accumulation area in this blue color, but here we have the ablation area. And there's an equilibrium line somewhere here separating the accumulation area from the ablation area. So this is the best or most detailed series of mass balance measurements available in the world, and it's been done every year, and they are still doing it. And I just found a record from 1945 to about 2000, and then they can make a time series of the winter balance, which is there. It's fluctuating a little bit. And the summer balance is also fluctuating. But what you see as the difference between those two, which is the net balance, it has been, if you follow this line, it's a negative, 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 and then suddenly a few years with positive, negative, positive again, and some positive years here in the 90s and negative, and I can tell you that it is very much negative nowadays, and that is the case on most glaciers. So this was there is another way of presenting these results, and that one way of presenting it, that is to show the mass balance with the elevation. Then you have the elevation. This is the same glacier, 1,100 meters and up to 1,700 meters. And we have the winter balance. If we start here, we draw a mean value for every elevation band, like that, and we have the winter balance, which is here, and it's a high number, 3 meters or something like that. Here in the upper parts, 3 meters of water, and then it's getting smaller and smaller, and down to about 1 meter here in the lowest part of the glacier. Then we take the summer balance. There is, well, if we start here, for example, in the lowest part of the glacier, it's losing 3 meters, almost 4 meters. But when we get at higher elevations, there is smaller ablation, but there is some ablation all over the glacier. Even in the highest part, it's melting a little bit. So it's about, well, half a meter or something like that, which is lost here in the upper part, but then almost 4 meters down here. And then the net balance is the difference between this curve and that curve, and that would be here, and this one. And here we see that at an elevation of 1,500 meters, we are moving from positive mass balance to 0. And then at lower levels, we are at minus. There is loss. So here we have the result that the equilibrium line, when there is equilibrium between mass, well, gain and loss, and the mass balance is 0, then that is at 1,500 meters, and above we have the accumulation area and the ablation. And it's often, if you read literature about the glaciers, it's often discussion about the slope of this line, especially in modeling, that you don't have measurements like that, but you may have some idea of the net balance gradient, and then in your modeling you're using a straight line like that as a measure of the net balance, and it is different from one glacier to another, and from one climate regions to another, what the slope of the net balance gradient. So that is the balance gradient with elevation. And now this is given as a specific value, as meters water equivalent. But if you are interested in describing this as in the units of volume of water, cubic meters per water, then you can multiply this curve, or all the 3 curves, with the area at any elevation. So then we have the winter balance in volume, just by multiplying this with the area at every elevation of the glacier. So here we have another presentation of the same. So the glacier is, and yes, so this is the net balance and summer balance. There's a lot of water produced by melting here at about 1,400 meters. So there's a lot of information here. And you don't see that here, but the area of the glacier is so large at around 1,400 meters that it's obvious that from this that you gain a lot of meltwater from that elevation band, because the area of the glacier is so large at that. So there is more information, well, different information in this than that. So that is well, there's another example. You can just say that you're going from a point value. Well, there's another example. You can look at it in the slides which you will. So here we have an example of mass balance with elevation. It's not so detailed as I think this is one from Iceland. And we have the accumulation curve here. 0 is there. This is so this is the winter balance, and this is the summer balance, and the difference is the net balance. 0 is there. Well, it's about 11 at 1,200 meters, the equilibrium line on this glacier. And then we have the area distribution with elevation, or sometimes called the hypsometric curve, area distribution with height. And you multiply the two. Well, or you're doing the integral over area of this specific value. So you get this in the net balance variation in cubic kilometers per year. Sometimes I write A for and sometimes I am writing IR. Well, this is Latin, annum, and year is something. So don't let that confuse you. Okay, so now we are here. We have now we know a lot about the glacier. We know that in the accumulation area, the balance is positive. In the ablation area, it is negative. And the equilibrium line is there. If we do the integral over the entire glacier, then the question is, what is the total balance? If it is 0, if this cancels out the gain in the accumulation area and the loss in the ablation area, if you integrate over the entire surface, then this is going to be 0, and the glacier is in balance. And but nowadays glaciers are not in balance, or there are very few. They are the total volume of ice integrated over the entire glacier during a glaciological year is in most places minus, so there is more ablation than accumulation. And then the glacier is shrinking, but in the case it's positive, it will be growing. This is obvious. And so I'm just stating the obvious fact here. We had growing glaciers. Well, we saw that there were a few years of positive mass balance in Sweden, but in general it was negative, and now it is every year negative in Iceland and most countries. So this is the most detailed type of mass balance measurements, but it's not practical on large glaciers, not practical in high altitudes. So it's so we have to try in many places other methods. Another method is called the hydrological method. And then you try to estimate the net balance of the glacier by measuring the total precipitation in the drainage area and the runoff out of the glacier. So this is just a continuity equation. This is gained as precipitation. This is drained out as water. And there might be some evaporation there. But anyway, we are listing up all the possibilities. And the net balance of the glacier, entire glacier, would be the difference between all the water added to the drainage basin minus the water drained out or evaporated. It's very rare that you can do this. You need a very precise measurement of precipitation, and it's not available. So this is just a possibility. Okay, so now we have another method, and that is to that people evaluate the elevation of the snow line or the fern line, just from aeroplane they fly over, or from satellites or whatever. In the autumn, at the end of they estimate the elevation of the transition between snow or fern and ice, and use this as an approximate estimate of the equilibrium line altitude. This is not a measurement in the field, but as you see from here, so we are trying to look at the line distinguishing between snow and ice. And in theory, this is the equilibrium line in our detailed measurements, but we are not able to go to the glacier. We are just flying over it, and we estimate from some kind of remote sensing the elevation of the snow line on the fur line. And so this is, now we are over to ex situ. We are not on we are outside the place doing this. And this is, so if you can do this from one year to another, you can see that it's changing. And nowadays, the elevation of the snow line is rising higher and higher on most glaciers. And so this is an indication of an indirect method of observing the changes in mass balance. Here is an example from Vatnajökull, the largest ice cap in Iceland. We can see here the equilibrium line. There's a dirty or ice part here in the lower, and this is from satellite. This is from a long time ago, and you can see the equilibrium line, and it's about 1,100 meters or something like that here. And so there's a large accumulation area in the center of this ice cap, and much smaller ablation area here all around. And this is another example. This is from remote sensing, simply This is from Norway, that they do the same. So don't, and you are familiar with that. There is one problem which I mentioned yesterday about you have to be careful about when you are assuming that the Fern line is the same as the equilibrium line, because you might, during the summer, get some refreezing of meltwater and superimposed ice formed on the glacier surface. And because the ice surface is cold and the water is percolating through the snow and refreezing and forming ice directly, so you get ice here on the surface. But this is so you are observing ice, and then coming in further on, observing ice. But this is superimposed ice, and it's first here that you start to see the fern. But this part here is indeed in the accumulation area, because this is a part of what was accumulated there and changed directly into ice. So you have to be careful, and in some places of the earth, you don't need to bother about this. There is no superimposed ice left in the autumn. But in other places, there is can be a large area at the boundary between the ablation area and the accumulation area, with a layer of ice, which is just what belongs to the accumulation of the glacier. And so be careful about that. That is, and then we go over to other methods, and they are, I'm running out of time, and they are often called geodetic methods, and they are just what you do there is that you observe changes in the surface elevation of the glacier. You can have one map of the glacier in 1 year and another map some years later, and you subtract one map from another, and you find the difference in mass between those two maps. And this is an estimate of the mass balance over the years between the maps, making of the maps. Also here you have to, what you are indeed doing is that you are looking at this continuity equation, so you are measuring the change in the thickness of the glacier with time, and you are, and this is caused by the balance. But it's not only that, it's the flow of the glacier is affecting the change in the elevation. But if you integrate over the entire glacier, you don't need to worry about transport of mass from one place in the glacier to another. So, but if you are looking at one spot, for example here, you can't use the difference in height, in elevation, or difference between the two maps. You can't use that as a measure of the mass balance at this point, because some ice may have moved into this place where you are looking at and affected the elevation. But as I say, so you have to be aware of that. So if you have maps over the entire glacier, you don't need to worry about that. But whenever you are trying to estimate this as a function of elevation, you have to consider whether at some elevation, the change might be affected by movement of mass within the glacier. And so here is an example from Iceland. We had the maps from 91 and 2, and we saw them, and we find the difference in thickness of the change over 10 years from a few meters up to 8 meters per year. So there's a lot of thinning here in the lower parts, in the red parts of this curve. And so this is an example of that. Then I will move quickly. It's you were late in the morning, and now I'm late finishing this. But anyway, and now the laser altimetry. There's another technique. Laser altimetry. It can either be from aeroplanes or satellites, and so you are emitting an infrared laser pulse that is reflected from the glacier surface. You are flying over this like that, and you are familiar with this, and here in India you are world-leading experts on the remote sensing, so you will learn much more about this than I can tell you. I'm just mentioning this because I'm talking in general about methods. There is a very interesting technique, the light detecting and ranging, or LIDAR, very, very accurate. And that is the same, it transmits laser pulses, and you fly over like this, over the glaciers, and you get the accuracy is better than 10 centimeters in elevation. So if you can do this repeatedly, you get a very good estimate of the mass balance change of the glacier. You can do it also in some small planes if they are available, with one propeller, and you need position, GPS, and a laser, and so on, and you fly. In this case, it was in Canada some years ago, or many years ago. They were just flying down the glaciers in the central line, and using this as an average value for each glacier. And the results they obtain is something like that. This is 1948 from an old map. This is 1996 cross-section of the glacier. This is 2000. And this is the difference, elevation change. It's in foot, because, well, anyway, I just got this from Keith Eckelmeyer, who was a glaciologist in Fairbanks in Alaska. He did this almost 15 years ago. And this is the one way of presenting these results. And then the most modern method is so-called GRACE method. It's the gravity recovery and climate experiment. This was launched in 2002. And what they do is that they have twin satellites. There are two satellites moving in the same orbit, and the distance between them is 220 kilometers. So they are moving together around the world, and they measure the variations in gravity. They use microwaves, and they're able to sense difference in gravity, which is affecting their, well, they are doing this together, but when one is over an area of higher gravity, it's affecting that one, not the other. So I don't know the details of this, but this is a very intelligent method of observing details in gravity, and they are doing this several times, well, every year, so they are doing this continuously. And so if the mass of glaciers is reduced, there's a change in gravity. So that is the idea. And but it is a little bit, it is complicated, because they have to do all kinds of, well, the gravity could be changed from different reasons. Some of the water produced by melting of glaciers might still be draining in the groundwater system or somewhere else. And so there is a lot of problems with this method. But what they came up with was that the Greenland ice sheet was losing mass at that rate. So from 2000 to 2010, the loss, this is centimeters water, so it's from 20 down to, or 20 meters difference as an average value over the 4 years until then, and then going on. So it's 20 to plus to 20 minus, so it's 40 centimeters average loss of Greenland over the area and over the 10 years period or so. And they are going on, and this is very exciting. I'm just finishing by summarizing the methods for the surface mass balance. In situ, which is on the glacier, we are snow probing, the density measurements. You remember ablation stakes. We get seasonal values out of this, or annual values, which is the only method to do that. Or, well, you can maybe hire a laser, an aeroplane every spring and every autumn and so on, but it's very expensive. It may be the future. It's labor and time intensive, so it's not practical on large size masses. Then you have the hydrological method. You just measure all the water going into the system, which is not possible. It's just a nice idea. It's very difficult to do this. Then you have geodetic, as they are called. You are measuring surface elevation changes, but you are not measuring the density. And when you are subtracting one surface from another, you get a volume. The question is, what is the density of that volume? And so when you read this, you see a lot of discussion about that. What kind of density are you using, or how are you solving that problem, or are you just assuming that it doesn't really matter in the long run whether this mass is considered to be pure ice or snow of a certain density? So it's a problem that you don't know the density, but you have kind of repeat photogrammetry. It's quite interesting. You look at some photos taken half a century ago, and you take a new one, and you can use it to estimated change. Airborne satellites and so on, LiDAR. And you can measure many, many glaciers over short time, so it's very effective in that way. You can map the firn ice transition, you can change in the equilibrium line, and you can use the gravimetric method, the grays. So this was my talk about this, but others will talk much more about this during the course. And in the afternoon, I'm trying to make some very simple problems just to get used to these terms. So isn't that at 3 o'clock? Anyway, it's in the afternoon. So now it's okay. So now you can ask, yes? More than one. More than one ablation area for a given glacier. Well, yes, it's a possibility. Yes, that. Well, we know the definition of okay, I'll just. What I am drawing here is a very simple. I'm drawing a very simple example with one ablation area. But but I would say that well, you could have some tributaries with which are different. But I would say that in general you have only one ablation area. But I could, however, point out that it's a possibility to have two accumulation areas, and that is in some places there is so much snow drift to the margin, towards the margin of the glacier, that you cannot melt all the snow piled up here in this lower part. So at the end of the summer, there is still something left of snow here. We have seen that in some places. So the accumulation area is here in the upper part, but there is something left of the accumulation in the lower parts. But well, I'm open for if you find some places with several. That would be a little bit strange. Well, if you have, it's possible that you have some dust falling on the glacier here in the accumulation area, and so high melt rate that you will melt all the accumulation in a spot here, and then you have an ablation area here where you can think about that. If you have a volcanic eruption spreading ash on a limited area here, so you have much higher, or some black carbon or whatever, dust from industry or whatever, increasing in a spot, the melting in a limited area here. So in the end, you will be losing mass in that at that level. I am. If the glacier goes in different direction, yes. Yeah, why not? I mean, Well, now you know the basic principles, and now it's up to you to have the fantasy to think about all the possibilities. I mean, the question is the mass balance positive or negative? And so anyway, that is the only question. All the criteria. So, and if it is negative, it's an ablation area. If it is positive, it's an accumulation area. So that is there are, I'm sure, the glaciers in the Himalayas there are many discoveries there. So if you go there, you can discover many things which I have not fantasy to think about them. But with this basic criteria, as I say, you can find your answer to that. Okay, yes? Sorry. Okay. Okay. Okay, yes. Well, the question is about the mass balance and the retreat of the glacier itself. It is, so we have just talked about the mass balance, and the question is, what is the response of the glacier to that? Well, it's obvious that if it is losing mass one year after another, it will affect the flow. And so we were talking about glacier in mass balance, if we just start with that. If it is in mass balance, it's compensating at any time for the loss by flow of ice to and that is the glacier mass balance, and the flow and the mass are in balance. So, that is an ideal case, and as in all the physics we talk about, let's look at the steady state condition and this ideal case of a glacier, which is in mass balance, and the flow is exactly what is needed to compensate for what is lost here, and the glacier surface is the same all the time in that case. Yes, okay, that's a point to be mentioned, that we are accumulating every year mass here on the top, and so you might ask, why does the glacier become steeper and steeper every year if you're always adding mass to that? And the answer is that the glacier starts to move. And so the surface in a glacier which is in balance would stay the same all the time, because it would move exactly what is needed to do the job of, to transport the mass which is accumulated here down glacier. And the same here in the lower part. The surface would look the same all the time, even though there's more melting here than accumulation, because ice is moving continuously up to there to compensate for the. So this is a glacier which is in mass balance, and it will just stay like that with no change. But then to the question, if the glacier is losing mass, the balance, the balance is negative, okay, so that's what we were saying. The glacier is in mass balance, it's just looking the same all the time. If it is negative, then there is not enough production of mass in the accumulation area to compensate for what is melted here, and it will obviously retreat. So it's shrinking in volume, as I say, but it is also retreat. You are not moving enough material down to compensate and keep this surface as it is in a steady state condition. And the other possibility is that you are adding more mass to the glacier every year, more and more, and then you would increase the flow of the glacier down glacier, and you will do better than compensating for what is melted and add continuously to this, and the glacier will advance. So the mass balance and the response of the glacier is what you were asking for, and we will tomorrow or maybe on Monday go over to the movement, because this mass balance is driving the movement. So next step in glaciology is to learn about the movement of glaciers. So this was exactly the question to ask. Okay, and more? No, if not, we will meet later on and others take over now. So, okay, thank you for this. Okay. Yeah. Yes. No, you can have a basin like that, and the glacier is only one part of it, and then a river coming out like that, and you have a station here for measuring the discharge, so you have to. But if you have a gauging station here, that would be good. But in most cases.
And if we consider here, then
Yeah.
many processes are there also, like infiltration, soil moisture, and
Oh yes. So what I was pointing out that is a very difficult problem. So it's almost impossible. So I was just mentioning this as a possibility, but as you point out, it is. It's hardly practical.
30 minutes will go. Yeah, take 11:30. Okay. Can you all hear me? Huh? Okay, so you don't need, this mic need not be turned on, right? Is it okay? Okay. All right, I think I think I'm going to continue with the system level presentation. So I think many of you must have heard about feedback, right? Feedback. What are the feedbacks you have heard about? Oh, that is in the electrical circuit, right? No, but actually the concept comes from, I mean, maybe not the concept, but mathematical treatment of feedback in climate system actually comes from electrical engineering. Because electrical engineers had already known this amplifying, right? So same concept is actually used here as well. For example, how there is a small climate change, how it can be actually amplified by physical processes. So this is actually a very interesting quantitative topic, and I think anybody who is who has either science or engineering background, and also who wants to understand climate change, I think this is a must to, first of all, to have some knowledge about the feedback in the climate system, because this is really a major uncertain area as well. So let's first see the context for this. Okay. In fact, since 1990, this is a very simple question, but I would still put this is one of the grand challenge in climate science. That is, suppose you double atmospheric CO2 concentration in the atmosphere. You just double the atmospheric CO2 concentration. We all know that there is a greenhouse effect, right? The outgoing long wave radiation is trapped. Because of that, there is a heating of the system, and because of that heating, eventually the climate system will warm, and let us say we just say wait for whatever time required. It could be 10 years, or it could be 20 years, or it could be 100 years. Finally, the system reaches a new equilibrium, right? In that new equilibrium, what is the temperature change? Do we know that? This is a very simple classical problem in climate change. You double atmospheric CO2 concentration, what is the equilibrium climate change? So very interestingly, even the 25 years back, there was a model comparison. People use different models, and there was a range. It could be anywhere from 1.5 to 4.5 degrees Celsius. Why is that? We can't be really certain about this. There is a huge spread. You can see that some people are saying, some models are telling the warming for a doubling could be about 1.5, but there are some models which show 4.5. So where does this difference come from? Where does this difference come from? So we will see the reason for this. Now, in the latest, this is a 2014 result. So there is a new set of models, CMIS 5. I'm sure that some of you may be using this CMIS 5 data for your climate work. So here, the new result is 2.1 to 4.7. Again, you see this, there is a huge range. The lower number has slightly increased, but the upper range has remained the same. So I think the bottom line is there is a huge uncertainty in climate change, even for a very simple problem, just double the atmospheric CO2 concentration. But think about real world. There is, of course, so many things going on. You have aerosols, you have land cover change, you have solar activity, you have ozone changes. There are so many things. But this is the very simplest problem. Even here, you can see there is a huge uncertainty. So now, what is the reason for this? So I have written next the gain factor of 1.5 to 4.5 in this slide. So suppose, let us say there is no feedback in the climate system. One can mathematically show that the temperature change should be only 1 degree. Suppose there is no feedback in the system. The temperature change should be only 1 degree. So the fact that the models are simulating 1.5 to 4.5 means there is an amplification factor of anywhere from 1.5 to 4.5. So the climate system has an amplification factor. This could be, I mean, of course there is a range, but all the models are telling there is definitely a positive feedback. Okay? Without feedback, we should be having only one. The temperature change should be only one. Now, how this is relevant? I'm sure some, have you all seen this graph? You know, basically the atmospheric CO2 concentration and the temperature. I mean, this is the temperature and Antarctic temperature in the last almost 1 million years. So you can see that the CO2 concentration has fluctuated anywhere from 180 ppm to 280 ppm. But the current CO2 level is of course here. For the, you know, in synchronization with this CO2 change, you can see that whenever you have higher atmospheric CO2 concentration, there is higher temperature. So the temperature is actually almost, you know, look at this change, almost about 8 degrees. So the Antarctic temperatures have fluctuated by 8 degrees Celsius. In fact, when you convert that to even global, you know, using some kind of tool, you can infer what is the global mean average temperature. Again, you know, you get a close to 4 to 5 degrees. So, with, you know, but the amount of CO2 fluctuation here only is 100 ppm. So even if CO2 is driving this climate change, you cannot get a climate change of 5 degrees for CO2 alone if it is responsible. So the reason such a big magnitude in temperatures you see is because of feedback. So the main feedback in this case, it is believed to be ice albedo feedback. So I'll explain what is that next. I mean, okay, so just a very basic introductory concept. What is feedback? So here is the definition. Feedback is a process whereby an initial change in a process will tend to either reinforce the process, right? Suppose, you know, your initial tendency is to warm the climate, but if there is a process that basically leads to additional warming, then that's called positive feedback. If there is a process that tries to weaken that initial tendency, then you have a negative feedback. That is basically damping. So that is, I mean, you know, many of you know what are the positive feedback, like, you know, water vapor feedback or ice albedo feedback. Can any of you tell me a negative feedback? I mean, in the real world, for a climate change problem, how is that negative feedback? Aerosol is a forcing. Yeah, black body radiation, for example, as you warm the system, the response of warming is what? Just in, you know, emitting more OLR, more outgoing long wave radiation itself actually is a loss to the system, right? Suppose you increase the temperature by 2 degrees. We all know that the black body radiation is directly proportional to T power 4. So the system will actually lose more energy. So this is actually called temperature feedback or Planck's feedback, because this comes from Planck's law of radiation, right? So the temperature change itself is actually a negative feedback. The increasing temperature itself is a negative feedback, okay? And another good feedback, which is, of course, could be operating on a longer time scale, is this is not exactly the physical climate system. For example, you know, you increase atmospheric carbon dioxide, right? The plants doing photosynthesis, that is actually a negative feedback because they are taking up carbon dioxide. As you put more CO2, plants actually like CO2, so that, you know, this is what is called CO2 fertilization. So if you increase CO2, the photosynthesis will increase. So that by that, the atmospheric CO2 will go down. So anything that basically prevents the initial tendency is negative feedback, okay? So here is a simple schematic, right? So let's say, you know, you could have, in the case of, you know, suppose this is the initial perturbation. If you end up this way, that is basically positive feedback, because you can really, you know, hypothetically you can kind of get into a situation, singularity kind of situation, but that doesn't happen because usually systems have both positive as well as feedback, I mean negative feedback, okay, both are combined and you kind of stabilize somewhere, right? So this is a case for this, of course. You know, you have a negative tendency this could be warming and this could be cooling, right? So, for example, ice albedo feedback, a good example could be, let's say, how do you create a snowball there? Suppose you reduce the amount of sunlight coming in. If ice albedo feedback is triggered, you can end up with a planet that is basically cooling, right? So just opposite of that. So these two cases are basically negative feedback because they are trying to prevent the original tendency. Okay, so here is this is albedo. This is a schematic for this ice albedo feedback. So initially, in this illustration, suppose you initial change is tending to cool the climate. Then because of that, you have more ice and snow with higher reflectivity. That could lead to less solar radiation absorbed at the surface because more sunlight is reflected. So this could be leading to greater cooling, right? So eventually, you can see that, for example, you could actually get a temperature change here. So this temperature change is the one that is without any feedback. But you can see that because of this smaller loop, you actually produce additional temperature change in the system. So that is basically the feedback, the temperature change that is related to the feedback. So you can really split the temperature changes into multiple components. For example, the first one, that is the actual, what we call as, temperature change without any feedback. And then you can actually really create multiple loops starting from here. Some feedback could be negative, some feedback could be positive. All of them contribute to the eventual temperature change, right? So the more recent one, that in the last couple of decades, people have been at least warning us about is what is called this permafrost feedback, because I think yesterday I briefly talked about this in the high latitude cold region. The soil is frozen, so the organic matter in the soil is basically right now prevented from decomposing. So once warming becomes, crosses particular thresholds, you would probably melt those soil layers which are right now frozen. This happens mostly in the colder places. I'm sure there is some permafrost in even our own Himalayas, and we do have, I think, major permafrost is in Siberia and Alaska. So those places, when the permafrost thaws, you are going to have both methane and carbon dioxide released into the atmosphere. Now what's going to happen is this carbon dioxide is an additional carbon dioxide that could provide further warming. So further warming will lead to further permafrost thaw. That's going to lead to additional carbon dioxide emission and additional warming. So you can have a kind of loop going around, right? So that is a positive feedback. Now, I think yesterday we briefly talked about cloud feedback. So you can see clouds are of course very complicated. I think there is nobody, we can't deny that fact. But in the latest report, I think there is a kind of they are all converged. If you read this report, it claims that most of the the net effect of all the various feedbacks associated with clouds is kind of positive right now. So I think what are the positive feedbacks? For example, most of the models show that when there is a warming, the cloud altitude usually in the tropical area goes up. So if the cloud altitude goes up, you have actually additional greenhouse effect. And the other simplest feedback is most of the models show that when there is a warming, the low clouds are decreased. So that basically the low clouds are all dissipated. So that means the reflective power of this cloud is decreases. So that means the surface can absorb more solar radiation. So anybody who is interested, I think I would suggest go to this chapter 7 in IPCC report. So there is a very nice explanation of all this feedback. In fact, it's almost like a textbook material. All the IPCC reports are like textbook material. So if anybody is really interested in, let's say, specific topics in climate change, for example, you want to understand cryosphere, there is a chapter in cryosphere. I think it's probably better than any book you would see in the market, and also later. Okay, so this is a kind of a summary plot of all the feedback that we know right now for the climate system. So let's look at one by one. Long wave radiation. This is the temperature feedback that I was talking about. That is a negative sign. So basically, more temperature, the planet has more temperature, it will radiate more and it will lose more energy. And then there is also additional feedback called lapse rate feedback, which see is basically when the climate warms, the lapse rate of the atmosphere actually, the atmosphere gets more stable. And more stable means what happens is the upper levels warm more than the lower levels. So the upper levels can easily radiate radiation. So that is also a negative feedback. So that lapse rate. And you can see plus, which means we don't know right now. I mean, that's kind of, let's put it that way. Here, we don't know exactly. It's definitely positive, right? And, emission of non-greenhouse gases and absorption, for example, because of climate change, there could be changes in the area of wetlands and things like that. So again, there is uncertainty here, plus or minus, ocean circulation, plus or minus. I mean, ice albedo is definitely a positive feedback, permafrost is positive feedback, and then there is also a air change. Here is a negative feedback. What that means is you put more CO2 into the atmosphere, more CO2 goes into the ocean. So the ocean solubility basically tries to reduce the amount of CO2 that stays in the atmosphere, so that's a negative feedback. And also there are time scales associated with each of these feedbacks. Some of the feedbacks operate on very short time scale, and some of the feedbacks do not operate on shorter time scale. For example, let's look at only the shortest and the longest. Long wave radiation and lapse rate feedback, water vapor clouds. So these are all feedbacks that can operate within a day or so. You increase the temperature of the planet, it will immediately radiate more radiation. Similarly, you increase the cloud, it's immediately going to scatter more radiation. But what about feedbacks associated with ice sheet? It takes millions of years to build ice sheets. So the feedbacks associated with ice sheets could be operating on hundreds of thousands of years. For example, the previous slide I showed you about this 800,000 year glacial interglacial cycles. Those are ice albedo feedbacks that operate on thousands of year time scale, not on a shorter time scale. That's where ice albedo feedback, particularly ice sheets plus albedo feedback. Okay, so you can see the bigger, okay, there are, I think here they go up to only centuries, not beyond that. I'll show you some feedback that operate later. So some of the key concepts anyway, to at least to get a broader view on climate change are these important, I mean, you should really have a very good physical insight into these, these concepts here, radiative equilibrium and budget. I'll just show briefly, one or two slides for each of them. I mean, I hope all of you know what is the greenhouse effect, but again, I will try to explain in a simplest way how using, what you have learned in physics, okay, radiative forcing, climate feedback, and maybe if we have time, some mathematical analysis of the feedback. All right. So I think I'm showing maybe this figure third time. Basically, if you go back to pre-industrial time, there was no anthropogenic forcing, and the climate system was in radiative equilibrium. Basically, the absorbed solar radiation was exactly balanced by the outgoing long wave radiation. Again, remember, these are climatological statements, which means only on an average. These are, maybe if you take the data for 30 years, it is true. In fact, if you take individual years, the system will not be in equilibrium, because for that particular year, the ocean might have stored some heat, or ocean might have released some heat. So all I'm talking about is valid over an average of about at least 30-year period kind of stuff. Okay. All right. So I'm sure if you have taken any of the introductory climate course, you would have seen a energy flow in the planet. For example, energy is coming in, short wave is coming in. It is reflected by the gases, clouds in the atmosphere, some of that, and some of that is reflected at the surface. And most of the absorption actually takes at the surface, right? And then, okay, so this is the short wave branch of the energy flow. So you can see also there is actually significant absorption of short wave radiation by the atmosphere. I think you can see 2/3 here. This is almost 78, and this is 160. So there is significant absorption of solar radiation in the atmosphere also. Okay, and then this is the long wave branch. But I think I just look at the final numbers here. For example, in the long wave, you can see that approximately 240 watts per meter square is going out. And if you just subtract these two, you will get similar number. This is the incoming reflected. So the total absorption of short wave radiation is kind of equal to the outgoing long wave radiation. I think the greenhouse concept you can see from here itself. You can see, is emitting this much radiation, right? And look at the huge amount of back radiation coming to the surface, because the atmosphere itself is a black body. So it is emitting a lot of radiation back towards the surface. So if you want your surface to be in equilibrium, now, see, if you didn't have this atmosphere, what would have happened is whatever this surface is emitting, it would have directly gone, right? But because you have this black body here, there is, look at this number, 390, this is about 400 watts, and this is 330 watts per meter square. So, enormous amount of back radiation, and because of this back radiation, your surface has to be warmer. There is no way, right? You can just calculate the temperature without that back radiation and with the back radiation, and you can, the back radiation has to lead to an increase in surface temperature. Okay, I think should we really be concerned about climate change? The greenhouse effect is, I think many times when you talk to people, several times people ask, what is this greenhouse? Is it really real? Or just, some kind of fiction that scientists have designed, right? It is, in fact, greenhouse effect is not a new thing. It is already existing. Even without interference in the system, greenhouse effect exists, because without the greenhouse effect, our planet will be really freezing cold. We would be having a planetary average temperature of, at the surface, minus 18 degrees Celsius, but we have not right now 15 degrees plus Celsius, because of the greenhouse effect of the atmosphere, the existing atmosphere, that, there is water vapor, right? And then there is even natural carbon dioxide, methane, right? Even in the pre-industrial time, the carbon dioxide in the atmosphere was about 280 ppm. So what we are really concerned about is not the greenhouse effect itself. We are really worried about the enhancement of that existing greenhouse effect. I think that is a real climate change problem, right? Okay, so here is a very simple way to understand greenhouse effect. Suppose, let's say you have a radiometer, fixed to a satellite. It is measuring the long wave radiation that is emitted by the surface of the planet. So if there was no greenhouse gases, you would actually, for the current temperature of the planet, the radiometer should be receiving this black line, because black line is according to the Planck's curve. If you remember your Planck's curve, that black curve that you see will be the radiation that will be measured by the radiometer. But what is happening now, because of the greenhouse gases, what happens is, this is for the current atmosphere. There are gases, they absorb at selective wavelengths, right? So the spectrometer measures this black line. It actually measures this red line, right? For example, carbon dioxide absorption here, right? So the radiometer is not going to measure, the full thing. It is going to the red line. That is actually the absorption by that particular gas. So in fact, the difference between these two curves, you can quantify. You can say that that is actually the greenhouse effect. If you want to say some quantitative numbers about greenhouse effect, in temperatures you can tell its magnitude is 33 degrees Celsius, because if we didn't have greenhouse effect, our planet would be minus 18. But today it is plus 15, and the difference is because of greenhouse effect. Or the difference here, this difference actually, I can go and tell you, just a minute. For example, you can also quantitatively say greenhouse effect in the other way. If you see, for example, the surface is emitting 400 watts per meter square, but how much is going out? Only, let's say 240. So the difference close to 160 watts per meter square. So you can say that in terms of energy unit, the greenhouse effect amounts to 160 watts per meter square, right? So let's finish the lecture. Just to hold on to your question, we will. So the bottom line is effect itself is of concern, but the enhancement of it due to increasing levels of greenhouse effect. So, you can also identify how do we actually estimate the greenhouse effect of various gases. I mean, you must have heard that, in fact, some of you must have heard that, in fact, water vapor is much more powerful greenhouse gas than CO2. How do we know the numbers? For example, I mean, today we have what we call as the radiative transfer models, so you can use them. So here is a calculation. It says what you can do is in a model, you can actually, in a model only you can do. In the real world, it's difficult to do. So in a model, you can take a model, you can put CO2, and you can make a simulation with CO2 and another simulation without CO2. Similarly, you can do a simulation with water vapor and without water vapor. So the difference between those two simulations is going to give you the net effect of whatever gas you want to study. So if that way, for example, let's look at this. Long wave radiative forcing of water vapor is actually 75 watts per meter square. So by putting water vapor into the atmosphere that corresponds to today's level of water vapor, you can trap, the planet actually traps 75 watts per meter square. On the other hand, you put the pre-industrial level of CO2 or present day level, I think this is corresponding to 1990s level CO2, you can see the trapping capacity of the amount of CO2 in the atmosphere is 32 watts per meter square. I mean, this is absolute trapping by these gases. So if you compare these two numbers, you can see that the trapping by water vapor is actually much more. So in the current atmosphere, water vapor has more greenhouse effect than CO2, right? And one can also, what is the, long wave trapping capacity of clouds, right? So that turns out about 30 watts per meter square. So clouds actually have a greenhouse effect of 30 watts per meter, right? So one can also, all these calculations I think shown here, they are for long wave spectrum, but there are also gases that absorb, for example, in short wave. For example, black carbon, it absorbs in short wave. So you can make a similar calculation for various gases in short wave spectrum also. For example, in fact, even carbon dioxide has a slight absorption in short wave near IR. Okay, so but it's much smaller compared to this long wave forcing. All right. So what is I think this is how many of you have heard about radiative forcing? I see few hands. Okay, good. Okay, so here is the definition. I think you can simply think of this way. I think for example, it is easier to describe in a model world. Let's say you have a model climate model. You can basically prescribe to that model atmospheric composition corresponding to pre-industrial world or atmospheric composition corresponding to present world. Now, whatever is the energy flux difference you see at the top of the atmosphere, that basically is the radiative forcing. For example, you can, what is the amount of trapping that has happened because of atmospheric CO2 concentration increase in the industrial era. Now we call that as radiative forcing. For example, I'll come to the numbers. Let's read this here. So change to the net radiative flux in watts per meter square due to any climate change causing mechanism. The change can be in either solar or long wave fluxes, right? Radiative forcing is also now, sometimes we call this also climate forcing. So it could be because of greenhouse gases. For example, you can think of this way. You can run the model with pre-industrial CO2 concentration, and then make another simulation with present day concentration. Now what you will see is with the present day concentration, the amount of long wave that goes out from the top of the atmosphere is going to be slightly less, right? Because there is IR trapping. Because you are now having less loss of radiation to space. So that is equivalent, of course, heating. So that loss is now rightly, if you calculate for today's concentration, it's roughly about 2 watts per meter square. So then what we say is the radiative forcing from CO2 since pre-industrial time is about 2 watts per meter square. So you can do a very similar thing for aerosols. You can prescribe aerosols corresponding to pre-industrial time, and then another simulation with aerosols corresponding to today. Are you going to get negative? Are you going to get negative radiative forcing or positive radiative forcing? In this case, aerosols. because what's going to happen is when you put more aerosol, there is going to be more reflection of short waves. That means the system is losing energy, right? If you don't have that aerosol, that energy might have been absorbed in the system, that particular short wave. So the simplest way is whenever there is energy gain because of a change, you call that as positive radiative forcing. Whenever there is a energy loss, right? Suppose, for example, we cut forest and clear the land and make the land more reflective. So that is a negative radiative forcing because the albedo increase of the albedo of the bare ground increase. So you are reflecting more short wave radiation. So you need to actually to also, in fact, one thing to keep in mind is you really have to calculate the flux changes both in short wave as well as long wave. And then you combine them. If it turns out to be a heating effect, then you call this as positive radiative forcing. Else you call this as negative radiative forcing. So here is the consensus numbers for the industrial period. So for example, all the changes that have happened to the industrial era. So for example, this is the radiative forcing due to carbon dioxide. So that's almost about 2 watts per meter square, very close to 2 watts per meter square. And this is due to methane, N2O, other greenhouse gases, and this is basically ozone, changes in the troposphere as well as stratosphere. So in fact, you can see the stratospheric ozone has a kind of, in fact, negative side, and but the tropospheric ozone causes a heating, right? Basically, positive radiative forcing. And land use change because if you cut forest, as said, the albedo of the land surface could increase, so that could cause a negative forcing. Aerosols cause negative forcing, right? Because they reflect sunlight, so because of that you have negative radiative forcing. I think one thing, so this is the total forcing, right? So the total forcing is something, like 2.2 watts per meter square or something. So compared to pre-industrial time, the planet is actually for every square meter of land surface or ocean surface, it is absorbing something close to 2.5 watts per meter square. Now, in fact, you can calculate also by just multiplying the surface area of that, which is 5 times 10 power 14 meters square. You can really calculate it. So it's almost close to a petawatt. So the planet is right now getting heated at the rate of 1 petawatt. Peta is what? 10 power 15. So that much watt there is a heating rate because of our anthropogenic activity. That's a good easy number to remember. 1 petawatt heating rate. Right? Now, I mean, of course, the heating rate is increasing with time, right? Because if you go back 15 years before, the heating rate was not this much because the gases are increasing. So because of that, the heating rate is going up. But if you actually do a time integration of, let's say this is, let me put it this way. Suppose I put the heating rate, really, I integrate this also entire planet, okay? That number I call this as F. If I integrate this number from, let's say 0 to, sorry, to 1900, that is, let's say, the industrial era to today, that's pretty much the heat that is going into the system. That is the heating caused by human activities into the climate system. We will come to this integration with some actual numbers. People have worked out all these numbers, okay? This is not something that we are imagining and telling here. This is, this whole IPCC was created for this purpose. It actually brings all the scientists working in different institutions, different countries. They pool all the data, all the knowledge to come out with these numbers. And okay, one more important thing is if you look at this, there is very little uncertainty. These horizontal lines you see there, that shows the uncertainty in these numbers. So in general, greenhouse gases, the forcing from greenhouse gases have very little uncertainty. On the other hand, aerosols have huge uncertainty. You can see the aerosol bars. In fact, these huge bars are mainly due to aerosols. Okay, anyway, good to remember that the radiative forcing, the total anthropogenic radiative forcing today compared to pre-industrial time is about 2 watts per meter square or approximately 1 petawatts. Okay, so to this is basically, I mean, you can also, I mean, this PDF show, I mean, I showed, in the previous figure, there was this black horizontal line. They were showing the uncertainty. You can also show the uncertainty in this fashion here. So this is the okay, so this is the greenhouse effect. You can see that PDF is a little narrow, which means it has less uncertainty compared to the aerosol PDF. The aerosol, you can see, if you really take the mean number here, it's about 1 watt per meter square, so -1. So aerosols are causing about -1 watt per meter square, and the greenhouses are causing about +3, and when you combine, the net forcing is approximately about, the mean forcing is about 2 watts per meter square. Okay. I think, yesterday we had some discussion, somebody was asking about water vapor and all that. So in fact, there is a huge misconception. I'm not sure whether I will be able to clear that today, but if you look in the previous table, radiative forcing, obviously if you go and measure water vapor, the water vapor in the atmosphere has actually increased. But why it is not in the table? Water vapor is a greenhouse effect. It has greenhouse effect. It is a greenhouse gas. Why it was not there in the table? It should be exerting huge effect. Huh? Yeah? Okay, I think this is where, I think if you recall yesterday I was talking about, I think somebody in fact also after the lecture was talking to me about external and internal forcing. So this is important. Water vapor is actually not a forcing, it is a feedback. Right? Okay. Here is a, oh, maybe I missed that. Okay, I don't have the answer here. But remember, for example, similarly cloud changes, they are not. Similarly snow changes, they are not there. Similarly ice changes, they are not there in this diagram, in the radiative forcing question, because they are all part of the system. They are all feedback. So you have to really distinguish. It's very hard to in the early, period like you, but for you. But it's very important for you to distinguish between feedback and forcing. Forcing is something coming from external to the system, but feedback arises from changes in the internal components of the system. Water vapor is internal component of the system. Clouds are internal components of the system. Winds are part of the system, right? We don't really cause the change in water vapor. It is the temperature change in the climate system that causes the change in water vapor. Just like ice, how it changes? Because the temperature of the planet changed, the ice cover changed. So same way, water vapor in the system changed because of the temperature change in the system. So I think I've been reiterating this again and again. Water vapor change is very tightly coupled to the temperature of the system. Same way, ice cover in the system is tied to the temperature change. That anything that is tied to the, very strongly coupled to the temperature of the planet, you can, it's one way to understand this. They are part of feedback. They are not forcing, okay? All right. Now, I think let us have some brief idea of, the part of feedback, how they can actually amplify climate change. So before that, some real world issues. What happens when there is a sudden forcing? I mean, so definitely balance is not going to be, anymore true. So this n is not going to be 0, right? So n becomes actually, so when you instantaneously, let's say double atmospheric CO2 concentration, I said the outgoing long wave radiation will be reduced. So that is equivalent to energy gain for the system. So how much is it? We, in fact, there are even formulas to calculate this. So it is roughly about 3.5 watts. So if you double atmospheric CO2 concentration, this is, so don't confuse this number with the 2 watts per meter square that I showed in the radiative forcing table there. That number corresponds to carbon dioxide changes from pre-industrial time to present day. But this number corresponds to a hypothetical question where we instantaneously double atmospheric CO2 concentration. So you can actually increase the heat, basically keep the radiative forcing to the system by 3.5 watts per meter square. Now, Um, yeah, this is how the entire, I mean, if you ask me, very simple diagram for climate change, here it is. For example, it takes, atmospheric CO2 concentration was here, and you suddenly increase atmospheric CO2 concentration, right, CO2 level. I mean, let us say this is kind of doubling or whatever. Now, what happens is, immediately you see this is the original energy balance. Let's say you can imagine, this is where the net radiative fluxes were in the beginning. So because of this increase, suddenly what happens is the outgoing radiation decreases by this much amount. This is basically for a doubling of atmospheric CO2 concentration, about 3.5 watts per meter square, right? Because 3.5 watts per meter square is now not going out of the system. So this would be for a doubling, it will be about 3.5 watts per meter square. Now, you can see because of this, now, I think the climate change problem is the entire feedback and everything is dealing on this side of the curve. I think it is easy to understand radiative forcing. Now, after that, how the system adjusts, right? Now, for example, you can see that it takes, the global surface temperature slowly increases, and then it takes, there is no real time scale put here. It could be decades, it could be centuries. It depends on what kind of problem you are looking at. So that's why real numbers are not provided here. But after some time, the system is going to come to an equilibrium, right? So just like we have equilibrium, in pre-industrial time, when the net fluxes kind of balance, right? So what we have to really do after the climate system has adjusted, again, when the system has come to a new equilibrium, the radiative fluxes there in the atmosphere has to again balance. The numbers could be different. Right now it is 240 watts per meter square and 240 watts per meter square. After the system adjusts, it could be 242 and 242, or it could be 238 and 238. We don't know. I mean, I think that's where the feedback uncertainty plays a role. Okay, but eventually you can see that the system responds. Right? Eventually you can see that the net fluxes again go back to the original level. Right? But I have not here specified. I have only said net flux. This does not mean long wave flux. Right? It could be any flux. It could be short wave. For example, you can achieve the new equilibrium by reflecting more solar radiation, or the planet warms, and because of that you enhance the outgoing long wave. See, you have reduced the outgoing long wave radiation by 3 watts per meter square, right? Let's say 3.5 watts per meter square. Now, you have to go back to the original balance. What you can do is now, you can increase the outgoing long wave radiation from this point. You can increase by 2 watts per meter square and increase the reflected short wave by 1.5. Then you are again back to balance. So the response, I would say, this particular branch of the system is called the response of the system. So the response can be in the short wave, or it can be in the long wave. For example, because of this forcing, let's say clouds increase. So increased cloudiness will lead to more reflection. So that is basically the response. I think I want to understand this summation could be either from, the response could be from short wave, or it could be from the long wave. I mean, the very limiting cases could be the response comes completely from the long wave. Then in that case, this whole thing is only from long wave radiation. Okay. Okay. I have some very, just to illustrate this concept here, some schematics I have made for this purpose. The entire climate change problem, in fact, if you really want to understand in a simpler way, I'm sure most of you are aware of this. Suppose put a heating, mCp dT by dt is if there is a heating rate, right? This is my forcing. So this is how any system, if you take a bucket of water, if you heat it up, it's going to increase its temperature by this formula. This is a very standard formula. I think if you go to 11th standard textbook, you will see that. Now, I think what is happening is, this is the forcing, right? This is the forcing we are providing. But is that equation enough? It's not enough, because what happens is, you think about it, if you have a bucket of water and suppose I am radiating it and I'm heating it, but what will happen is as the bucket heats up, it's going to now radiate more. So there is a loss also, right? So I can put that loss here. Let's say this is the radiative forcing and this is the loss. So the simplest climate change problem is basically can be understood in this form. Now, I think what generally we do is we parameterize this. This is the response part. The good analogy, as I said, this is the heating of the bucket of water, and this is the enhanced radiation emitted by bucket. The bucket loses heat. So same way, Earth is first by getting heated up, but as the Earth's temperature increases, it's going to lose radiation to space. That component is basically written here. So we generally parameterize this like this. So what it says is, as the temperature of the planet increases, its response also increases. But remember that response tries to actually bring the system to equilibrium. In equilibrium, what will happen is, by definition, equilibrium, this is 0, right? At equilibrium, dt by dt is 0. So at equilibrium, delta R should be equal to delta, sorry, at equilibrium, delta R should be equal to delta F. So the response of the system should be equal to, so basically if you go back to the previous figure, this is the response of the system. This whole component is the response of the system. That response should be equal to forcing. Now, this response we have parameterized as lambda delta T equal to delta F. So this is at equilibrium. So in fact, if you know what this parameter is, then we can actually calculate just from knowing radiative forcing, we should be able to calculate the final temperature change if we know lambda. But do we know lambda? We don't know. This is where the whole, we have been working for the last 30, 40 years to understand this lambda. And if you remember the first slide I showed, for a doubling of atmospheric CO2 concentration, the temperature could increase by 1.5 to 4.5. That uncertainty comes from here because different models have different lambda. We don't know the real lambda of that. Okay. All right. So let's see these cartoons and understand, try to understand. I think I would say always think of a water bucket analogy. Think of this planet as a water bucket, then you may be able to, it's not exact analogy, but it will help you to understand. Okay. So this is the MCP delta T by, okay. So this is at any, I put this transient climate change. Transient means the system has not come to equilibrium. So you have a time dependence here, right? And here is the parameterization delta R equal to lambda delta T. Now, let's put it this way. This is the heating of the system. In the transient phase, what it is doing is the system is losing some energy, but that energy is not exactly equal to this. So because of that, there is a heat storage here, right? Whatever is the difference between these two, this is the heating and this is the loss of energy. So there is a small difference, and that small difference will go to heating the system. Now, what about equilibrium change? In the equilibrium change, this is 0, so the response has to equal to lambda delta T as I showed here. And in this case, the heating of the system has stopped. But remember, this system is now in a warmer state compared to the original state. But it is not heating anymore. That is what is called the equilibrium stage. So in that stage, whatever we provided as heating should be equal to what it is losing. So what is the case? Here in this case, you can again go back to the bucket analogy, and you are radiating the bucket, but the bucket has heated enough, so it is losing same amount of energy it is losing. So it is not heating up anymore, but whatever energy you are giving, it is losing it. That's all. Okay, so that is what is equilibrium climate change. Now, why the problem is so complicated? Now, here are the feedbacks, what the feedbacks are doing. So, what really happens is, in the equilibrium, we showed this in the equilibrium. I showed you that there has to be radiative forcing. The system is no more heating, right? And definitely, the system should be losing the same amount it is receiving. That is all true. But there are a lot of up and down arrows happening now. So now I cannot go back to the bucket analogy. Bucket analogy, there was no feedback in the bucket. But here, there are a lot of feedback. What's happening is, water vapor feedback is actually giving more energy into the system. Temperature feedback is actually helping to system energy, right? So, and lab state feedback is kind of helping the system to this, and then there are other feedback like this, right? So it is if I add up all these numbers, that is what I call as feedback, right? I mean, these are all, remember, this delta R is the response of the system, and the response of the system is in various components. So when I add up all these arrows that I have, they are equal to this delta R, not just the radiation. In the case of bucket analogy, only the bucket emitting enhanced radiation, that is equal to delta R. In the case of our real planet, delta R is composed of all this temperature feedback, water vapor feedback, ice albedo feedback, and everything. When you combine all of them, they will give you delta R. I think that's a very simplest analogy you can think of, right? In the case of water bucket, only this is present. But in the case of Earth, you have all these other things happening. So you can now decompose that lambda into many parts, and each of them correspond to one of the feedback. So this will be temperature feedback, this could be water vapor feedback, and lambda 2 could be ice albedo feedback, lambda 3 could be lab state feedback, etc. Okay? Okay, in the case of transient feedback, this delta R still has not reached the value of delta n, that's all, as simple as that. Okay, this is a kind of bit of complicated, I think I did actually talk about this here, but let's for the time being forget about it. Okay, distinguish forcing and response. So I think this is the same point I made about the water vapor feedback. So solar inputs, volcanoes, atmospheric composition, like CO2, methane, they are all forcing. They are not feedback. On the other hand, changes in internal variables are called feedback because they can amplify or damp the climate change. So for example, water vapor, clouds, ice, etc. They are all part of the system, and their changes are not made by us. They are made by climate change itself, right? Changes in water vapor that arose because of change in the temperature. Similarly, change in ice, it happened because of change in the temperature of the planet. So they are all feedback. Okay, I think if you remember, recall, I showed you a very nice schematic. In that, I already showed that delta R should be equal to delta N. So the entire, for equilibrium climate change, the total response should be sum of all responses, right? I think I nicely illustrated in that schematic. The response could be in temperature, response could be in water vapor, lapse rate, clouds, ice, etc. They are all, but I think mathematically what we do is, we try to express all of these responses in terms of watts per meter square, because the original forcing is in watts per meter square. So you can also represent the response also in watts per meter square. Okay, now, yeah, go back to this feedback analysis. So what happens when there is a sudden radiative forcing? So I think intuition tells me that the planet can get rid of that excess heat by warming, right? So that is the response. If no other feedback is present, temperature response is the only response, right? That's the bucket kind of analogy. So, but in the real world, it is not that simple. There are multiple feedback operating. So that allows multiple outcomes. We don't know what exactly is the, right? So climate response and feedbacks are actually synonymous in some sense. So So both are expressed in watts per meter square per Kelvin, right? Um, okay, so let's yeah. And I think I did actually, the beginning of the lecture, I showed one graph that shows the different time scales up to from hours to centuries. But I think I have again the same point here. For example, this is the stomata of the plant. If you increase the carbon dioxide, apparently the stomata can respond within seconds to minutes. It can respond, but the atmosphere takes about a year to respond. The deep ocean can take hundreds of years. For example, I think the very interesting point is, do you think if you go 3 kilometers below the ocean, imagine somebody who is living, the analogy looks absurd, but suppose somebody is living 3 kilometers in the deep ocean for the last 500 years. Do you think he would have seen climate change? No. So climate change has probably actually, if you see, the temperature warming is mostly confined to the last 100 years, only about 2 kilometers or something, 2,000 meters or so. So the deep ocean has not still seen, the ocean floor actually has not seen, so much change has happened in the surface of the planet. So deep ocean is going to take multiple centuries to eventually see that, because it takes that much time to take the heat down to the ocean floor, right? So in the same way, if you look at this ice sheet, for example, this is some model simulation. This is for Greenland ice sheet, for a quadrupling of CO2. If the atmospheric CO2 concentration is quadrupled instantaneously, apparently, even after nearly 2,000 years, some fraction of ice is still left. You see this ice here? So it takes almost, I think, 2,000 years for Greenland ice sheet to completely go away. So, but remember, this is also a response to climate change. So the ice sheet is going to provide a feedback for thousands of years. On the other hand, cloud and water, water vapor, they would have provided a feedback instantaneously. They respond quickly. But this responds over a time scale of, so that is why the actual warming, if you wait for 5,000 years, it could be way higher than 1 or 2 degrees, because they are also providing feedback, but these feedbacks are operating over 2,000 years. So, so the feedback themselves have different time scales, and if you wait long enough, the ultimate warming could be, who knows, it could be even 10 degrees for a doubling of atmospheric CO2. But that could take 10,000 years, right? So what is the net feedback as suggested by today's climate model? It has to be negative, because why? What is the net feedback? There is a net amplification. But if I include the temperature feedback also, it's actually, because temperature actually provides the biggest feedback, and it is a negative feedback. And ice albedo and water vapor, they provide positive feedback. Apparently, I'll show you some numbers later on. They don't completely cancel the temperature feedback. So eventually, if you add all the feedback, you do have amplification, but the net feedback, the lambda, is actually negative. The lambda itself is negative. Oh, okay. So here is a simple example, right? Okay. Let us consider equilibrium climate change. So multiple feedbacks, of course, contribute to the radiative response. The total response should be equal, but opposite to the imposed radiative forcing for stability and equilibrium, right? Okay. I think, let us say only the temperature of the planet change. Now, actually, this is a very simple calculation. You can show that only the temperature changes, you will get a number like about 1 degree warming you will get. See, so even the temperature response, I put it as a feedback. So it feeds back into the system. See, this is the doubling of atmospheric CO2 concentration that provides a heating of 3.5 watts per meter square. And this is the feedback, temperature feedback, that feedback. It should have the same number for equilibrium climate change. So this you can achieve by 1 degree warming. Right? Now, take a very simple example. Suppose we have only one more feedback, which is ice albedo feedback. No water vapor feedback, no cloud feedback. In that case, what happens is, let us say assume albedo changes by 1% per degree Celsius of warming. In fact, okay, so this is, I'm assuming all of you know a little bit about albedo since you are all doing this cryosphere here, right? Um, so this is how albedo actually makes huge transition from summer and winter in the high latitude. So this is a schematic for ice albedo, albedo feedback. I think I already showed this. So if you do that, apparently, so the delta T could be 10 degrees C. So remember, just by bringing in albedo feedback, you can show that mathematically the temperature of the planet can increase by 10 degrees as opposed to 1 degree warming for in the absence of albedo feedback. Then water vapor feedback, I think this is probably a schematic that you are already aware of. And cloud feedback, this is as I said, we actually still don't know the net sign of this feedback, whether positive or negative, we don't know that. But simple rule of thumb, high clouds usually provide positive feedback because higher the cloud, colder it is. So because of that, it provides greenhouse effect, very strong greenhouse effect. So, for example, on a clear day, sometimes you do see cirrus clouds. I mean, have you ever noticed sometimes there is a lot of, you feel there is a lot of clouds, but that day it is very warm. Because if you, next time you notice that, you would see that whenever you have very high clouds, they are kind of transparent clouds. When you have them, they are called cirrus clouds. That day is actually very warm because they provide very strong greenhouse effect. On the other hand, clouds which are like this, low clouds, they are very efficient reflectors, and because they are too low, the temperature is higher, they are not cold clouds, and they don't have significant greenhouse effect. So these clouds provide a lot of short wave feedback, and these clouds can provide very significant long wave feedback. Okay, maybe I think we are running out of time, so we could avoid this. I do have this analysis here. I think let me just show you this particular thing that we talked about. For example, how would you calculate the Planck feedback, the temperature feedback, where there are no other feedbacks present? So this is how you can, this is a very simple Boltzmann, Stefan Boltzmann law. The emission is basically sigma T power 4. So if you differentiate that, you get 4 times sigma T cube delta T. So this 4 sigma T cube is actually the response per degree of warming. Per degree of warming, you basically emit this much. So this number, if you evaluate, you get actually, this is called the reference case with no feedback. For a doubling of atmosphere CO2, you can actually show that this delta T, which is basically 3.5 divided by 4 sigma cube, you can calculate, go home and calculate this delta R. If you remember, for equilibrium warming, this should be equal, this delta R should be equal to the forcing, which is 3.5 divided by 4 sigma T cube, that is 1 degree, you get 1 degree, okay? Now, so in the case of no amplification, lambda should do this lambda 0 T cube, okay? Now, how to deal with the albedo feedback? You have, let us say albedo feedback, albedo decreases by 1% per degree of warming. You can express that mathematically this way. Alpha is A minus B T, like a linear equation, right? And minus because albedo increases for cooling, right? Or decreases for warming. That's why this minus sign. A and B are constant. B is 0.01 because 1% change you get for 1 degree of warming, right? In this case, you can show that delta T is delta N divided by, so the lambda is modified by this factor minus B S naught by 4, right? So here is a new lambda. So if you plug it in the equation, that this equation, lambda delta T equal to delta F. If you plug this lambda here, you can actually show that the warming is 10 degrees. Huh? Yeah, when you warm, albedo increases. So that leads to more solar absorption. Yeah, whatever I can think here. Okay, let's skip all this, beautiful analysis. These are actually very simple. Anybody? Okay, so here are the feedback numbers. I'll probably wrap this up. So the Planck feedback is anywhere you have a positive sign, that means negative feedback. So 3.2 is what it means is for every degree of warming, you are going to emit this many more watts per meter square, right? For example, if you warm the planet, what happens is for every degree of warming, there will be 3.2 watts per meter square going out of the planet. So that's a negative feedback. Water vapor, what happens is for every degree of warming, you are increasing the water vapor so that 1.8 watts per meter square is trapped. So that is the meaning of this quantity, watts per meter square per Kelvin. In the case of ice albedo, for every degree of warming, the albedo changes such that you reflect 0.3 watts per meter square more, right? Or reflect more or less, whatever it is, depending on the case. Lab rate, so if you combine all of them, total feedback is 1.4, and that is basically the negative feedback, right? Okay, I think we are pretty much done, right? Response is positive. Okay, I think I'll stop here. I do have, anyway, these slides will be, distributed to all of you, I suppose. Yeah, I think I'll stop here. So if you have any general feedback, you can ask me now. Okay, it looks like everything is very crystal clear today. Okay.
Okay, now you can hear me? Good. So I'll try to stay here, but please let me know if you can not hear or if you cannot understand me. Just raise your hand. I'll put my glasses on so I can see you. And but it is a great pleasure to be back in India and back in Bangalore. I will be talking about ecology on Monday, but today I'm going to talk about permafrost. So I'm going to try to get through in about 50 minutes or so. What is permafrost? Where is it? How thick is it? How old is it? How does it affect the vegetation? And then finally, what will happen to the permafrost in a warmer world, and what will the consequences be? So what is permafrost? Permafrost is permanently frozen ground. The definition specifies that there should be it should be for a minimum of 2 consecutive years. But of course, much of it is a lot older than that, as you will see. It refers to the thermal status or condition of the substrate, so that it is not necessary that water is present, but all the same, water is usually present, and a great part of the Arctic permafrost is very ice-rich. It is customary to divide the permafrost into sometimes 3 zones and sometimes 4 zones. So the northernmost zone is obviously the coldest. I'm talking about the northern hemisphere here. And there, permafrost underlays all ground, or at least over 90% of the landscape. The southern boundary of the continuous permafrost zone is around -8 degrees centigrade mean annual air temperature. And this is also the coldest permafrost, but it's still warmer than the mean annual air temperature. It's of the order of magnitude of about -5 degrees centigrade. And in addition to the continuous permafrost that is on terrestrial land, there is also a vast shelf of continuously frozen land that extends from beyond the coast, the northern coast of Alaska and Siberia, towards the North Pole. And this is on land that was dry during the last glacial period. As the climate gets a little bit warmer, you get to the discontinuous permafrost zone, the changeover at about -6 to -8 degrees, and that is defined as the zone where 50 to 90% of the ground is underlain by permafrost. And so the permafrost begins to get patchy. It stays longer in the north-facing than on the south-facing slopes. It stays longer in fine-grained material, longer than in coarse-grained material, and it stays longer unvegetated than on unvegetated land. Then you get to the sporadic permafrost zone, where the mean annual air temperature is at least less than -1 degree centigrade. The permafrost in this zone is just below the freezing point. It's quite warm, in fact. And it's defined as the zone where 10 to 50% of the land is underlain by permafrost. And then finally there is the isolated permafrost, where the permafrost is only where the conditions for its development and existence are most favorable. It is, in fact, it's a huge area. Yes, sorry. That is simple. It's just because the sun warms the southern slopes, the south-facing slopes, up more than the north-facing slopes. But the area that is underlain by the permafrost is huge, as you can see. It's a quarter, it's almost a quarter of the northern hemisphere. But if you want to get the total area of land that has frozen ground beneath it, this is obviously a little less, because part of the permafrost is discontinuous or sporadic or isolated. So if you calculate the total area that is underlain by permafrost, this is estimated at about 12 to 17 million square kilometers out of the about 23 million square kilometers of the northern hemisphere. And I hope you can see this. So this is a map of the northern hemisphere, and maybe I can use this. I think this is better. So the blue color here is the continuous permafrost zone, and it is the biggest zone. It is by far the largest area of land. In these calculations, land beneath glaciers and ice sheets it's not included, just so that you are aware of that. It's not included in the calculations. So there's a very, very wide zone in Eurasia, in Siberia. There is also the land in the northernmost Alaska, northernmost Canada, and the Canadian islands. And then comes the discontinuous zone, the sporadic zone in yellow, and then the zone of isolated permafrost. Here you see, well, I don't know if I should call this Himalayas or Tibetan Plateau. I'm not sure which is the right term, but this is the great mountain massif in Asia. And this is underlain by either discontinuous or sporadic permafrost. You can also see that in Scandinavia there is mountain permafrost, discontinuous or sporadic. And here is my country, Iceland, with a little bit of permafrost. I'll show you some photographs of that later. Now, you might think that in the Arctic, the permafrost is confined to the tundra, but that is absolutely not the case. The permafrost extends way beyond the tundra, in fact. Oh, I'll leave this out. I'll just use this. So if you look at the this, you see that the dotted purple line here. This is the 10-degree July isotherm. That is the mean temperature of the warmest month, which is July. And the green line is the tree line. And you can see that in the big continental areas of both America and Eurasia, these are very close together, so that the forests do not extend beyond the 10-degree mean July isotherm. But the permafrost extends way beyond that. Continuous permafrost extends a long way into the boreal zone, into the coniferous forests of Siberia. And the discontinuous permafrost also extends a long way south in Alaska and northern Canada, also into the boreal zone, into the spruce forests of Northern America. So in the extreme north, in the Arctic deserts, there is permafrost under all the land. And as you move further south, it gets gradually thinner and it gets more fragmented. So it disappears first under coarse substances, so that where there are unconsolidated and porous material that have very little water holding capacity, it disappears earlier in dry substrates than those that are water saturated, and it disappears first in those landscapes where there is little insulation, and by the insulation I am referring to the vegetation. So that is where it disappears first, but the conditions favoring permafrost are fine-grained material, peat or silt, and I wasn't sure if you knew what peat was, so I put a picture of peat. Well, peat is just layers or masses of plant remains that are only half decomposed, and they build up in wetlands because the decomposition rates in wetlands are slower than the accumulation rates because of the waterlogged conditions. So that you get these this built-up over thousands of years of half-decomposed plant remains, and this is used for fuel. I'm sure also in this country it was a very important source of fuel in Europe in earlier times, and still is in some places. So that where you either have peat, yeah. Is it a volume to volume? That is extremely variable. It's very, very variable. You can have permafrost that is 90% ice, and then you can have permafrost where there is no ice at all, and anything in between. But as a rule, the lowland Arctic permafrost is much more ice-rich than the mountain permafrost. Yeah. So fine-grained materials, silt or peat, favors permafrost. Materials that have great water holding capacity. Also when the ground is saturated with water, and finally when you have an insulating layer on top, when you have thick moss or thick litter. Litter is sort of dead plant material, thick turf that isolates the frozen lands beneath, and also where you have thin snow cover in the winter so that the frost can penetrate deeper into the soil. So, having said all this, permafrost remains longest in vegetated wetlands, especially in mires with a thick moss cover. Just to show you some photographs of permafrost, this is very ice-rich permafrost in northern Canada, and you can see the ice beginning here and continuing downwards. Usually the uppermost part of the permafrost is the most ice-rich. This is taken immediately south of the Brooks Range in Alaska, so this is still in the boreal zone, still with trees. Here there are frost mounds You can see that the trees are sort of leaning this way and that because the unfrozen zone on top of the permafrost is only shallow, so that the roots of the trees cannot penetrate a long way in. And here you can see where the turf is broken away, and you can see into the ice itself. Now, the characteristic landscape features of the southernmost boundary, or the climatic boundary of the permafrost, are hills or mounds that occur in mires and wetlands. And so, and can you see this? Maybe it's not very clear, but I was trying to trace the outlines of this palsa. Palsa is a term from Finland, and the palsas are found in parts of Canada, parts of Finland, parts of Siberia, and also in Iceland. This is a photograph from Iceland. And in Scandinavia and Siberia, they can be up to 5 meters high. In Iceland, they are rarely more than about 1.5 meters, but they can be quite big, so they can be up to 100 meters in length. And what is special about the palsas is obviously they occur in mires where there's high water table and peat, so that they rise out of the mire simply by virtue of the growth of the ice lens inside of them. There is hardly any transfer of solid materials. The palsa only rises because frozen water has less specific density than unfrozen, and the frozen lens attracts unfrozen water that freezes around the edge, and then the frozen lens grows. So they can either float in the mire so that there is an unfrozen layer beneath, or they may be frozen all the way through to the moraine or whatever solid material there is below the mire. So I don't know if you can see that this is doing some work on the palsa. So this is the palsa here in the foreground. They rise out of wetlands, so the wetland vegetation dies because the conditions are now totally different, and there will be a new vegetation will develop on top of the palsa that is more tolerant of the drier conditions, of a thin snow cover in winter, and much lower temperatures during the winter. And here we have dug the part of the palsa out, so you can actually see the frozen lens below it, so that this here, I'll come to this in a moment. This is called the active layer. This is the layer that thaws during the summer, and in this case, this depth here is about 30 to 40 centimeters. This is the frozen lens below. Now, I'm not sure if you can see this, but this is typical of these palsa areas. They are like a mosaic of ponds, wetlands, and palsas. So, like, this is a palsa here, and this is another one here, and the third one here. They are brown in color first after they rise out of the wetland, because then they just have the dead wetland vegetation on top, and then gradually other plant species will colonize. So on to the thickness. How thick is the permafrost? Quite incredibly thick in places, over 1,400 meters in those parts of Siberia that remained unglaciated at the last glacial maximum. A lot thinner, but still vastly thick in most of the continuous permafrost zone in the northern hemisphere, of the order of about 350 to about 650 meters. And then it gets thinner as you go further south. 1 to 50 meters in the discontinuous zone, and then, 1 meter, and then it sort of disappears. The thickness is related to the age, so that all of the very thick permafrost is also very old. How old is it then? Apparently extremely old in Antarctica, 14 million years old, even up to 20 million years old in the high mountains of Antarctica. In the northern hemisphere, the age is very variable. Some of it dates back to the Pleistocene. Certainly in those parts of like Beringia, those parts of Alaska, and in those parts of Siberia that were unglaciated at the last glacial maximum, where the very thick permafrost is, like in Siberia, that certainly dates to the Pleistocene. But in glaciated areas, it is possible that at least much of the permafrost is less than 10,000 years old, or at least less than 12,000 years old, so that the freezing of the ground set in after the Pleistocene glaciers had retreated. And finally, some of it may even be quite young. The permafrost in Iceland, much of the permafrost, like the features that I was showing you before, it is extremely likely that they date back to the Little Ice Age. So they were formed somewhere between 1400 and 1900 AD. So really not very old at all, but then also quite thin. The thickness of the ice lens in the pulsars in Iceland is usually between about 2.5 and 3.5 meters. So, onto the active layer. So the active layer is the top. It's the only part of the soil that melts during the summer or during the growing season. So on this picture it is here. The permafrost table is here. In the uppermost part of the soil there are fluctuations, annual seasonal fluctuations in the temperature, also decadal fluctuations, but as you move further down, the fluctuations become smaller, and then maybe at the depth of 10 to 20 meters, the permafrost is fairly invariant of the seasonal fluctuations. But the active layer, the uppermost part, is actually the only part of the soil that plants can use. So I thought this was rather neat. I was going to go through this. This is showing the annual cycle of freeze and thaw in the Arctic refuge in Alaska. So this is at about 69 degrees north. So we begin on May 15 in the very early spring, and the tundra is still completely frozen. And let me see, I had timed this. So there's still snow on the ground, and this is frozen ground. Okay. Okay. So this is frozen, but I don't know why this doesn't. Oh, I'll leave it like this. So, on June 1st, 2 weeks later, the snow is disappearing, but the ground is still frozen. And then the summer comes on the tundra, and the thaw is rapid in the beginning, so that even after just 2 weeks, the active layer has thawed down to half of its maximum depth. And then the summer goes on, and already by mid-August, autumn has arrived on the tundra. As you can see, the plants are no longer green, they are sort of brown in color. And now the active layer is still melting, but at a much, much slower rate, and it has now attained about 92% of its maximum depth. Then in September, the ground begins to freeze again, and it freezes from the top. There are below freezing temperatures, but it begins to freeze from the top, but it's still melting at the bottom. And it's not until mid-October that the maximum depth of the active layer is realized, but at that time, the frost has already penetrated a long way from the top. And then by November the 15th, the ground is completely frozen again, and it will remain frozen until the early June the next year. So how much is it that melts off the active layer, melts off the permafrost in the growing season? Well, in the high Arctic, 30, 40, maybe 50 centimeters, and then this gets thicker as the climate becomes milder. 1 meter, 1.5 meters, exceptionally over 2 meters further south, but normally about 1.5 meters. But apparently in the mountains, in the mountain permafrost, the high mountain permafrost, the active layer is both more variable, but is much thicker than is normal in the Arctic tundra. And apparently in the Central Asian mountains, 1 to 8 meters. And according to a review by Bockheim, you find active layer depths in the Central Asian mountains of less than 2 meters only in very cold climate, where the mean annual air temperature is less than -6. So this is just a sort of a summary. So the top, so we're going from, this is for northern Canada, for mention the stations here on the top. So this is the northernmost one. This is the mean annual air temperature, going from what, about -17 in the extreme north. This is the active layer depth, but like I say, it's exceptional that it would be over 2 meters in thickness in the tundra. It's not the general rule. And so this, here you can see how the permafrost goes from being extremely thick and under all ground in the north. There may be unfrozen bodies called talix underneath big lakes and rivers, and sometimes in other situations as well. And then as you get further south, the land beneath rivers and lakes remains unfrozen, and then the permafrost gets a lot thinner and more fragmented. So how does the presence of permafrost affect the ecosystems? How does it affect the vegetation and the plants? What I'm going to say here really refers to especially lowland Arctic soils. I think the situation is rather different in the high mountain permafrost because the active layer is so much thicker there. But these are terribly cold soils, really very, very cold. They heat up very slowly in the summer, and so the soil environment heats up a lot slower than the above ground environment. And these are soils that are very difficult for plants. They're very deficient in nutrients, and yes, just a very difficult environment. The presence of permafrost obviously limits the root depth, so that the roots can only penetrate as far as the thaw goes. The permafrost can also prevent drainage. So even if these are fairly dry regions in the northernmost parts of America and Eurasia, maybe only 300 millimeters of precipitation a year, they are still waterlogged. The lowland Arctic tundra is often waterlogged during the summer, and it's the same water that freezes again and again, freezes and thaws, but it can't get away anywhere because of the permafrost. It can't drain away. And so that it may create a false groundwater table, and the water, also because the climate is cold and the growing season is short, so that there is not much evaporation. So the soils remain waterlogged. And this is a really critical point when it comes to considering the impact of global warming on permafrost soils. These soils remain waterlogged, which means that aerobic bacteria that use oxygen, they are either absent or very few in those soils, so that there is anaerobic bacteria, but they are not very active, so that there is extremely slow breakdown of organic material, which means that peat accumulates because plant remains are added faster than they are decomposed. And if the peat dries, obviously it will, if the top dries, then it will, it's a good insulator. It will insulate the permafrost underneath. Research in all over the northern hemisphere now shows that permafrost is undergoing rapid changes. The active layer is getting thicker. The temperature of the frozen ground itself is getting higher. The permafrost boundary is moving northwards in the Arctic and upwards in the mountains, and there is increased catastrophic collapse. I will show you this in a minute. This is called thermocast, and it happens when especially ice-rich permafrost melts, so that the ground on top of it collapses. So I don't know if you can see this properly, but these are just examples from both Russia, Siberia, Alaska, Central Asia here, and this is showing increases in the temperature of the permafrost at the depth of 0 annual amplitude, that is below the level at which seasonal fluctuations occur. And this is not the same depth in all the graphs. It's between 10 and 20 meters. So that there is evidence in almost all of them that the temperatures are increasing. And on the Tibetan Plateau, the lower limits of permafrost have moved upwards 20 meters in the north, and 50 to 80 meters in the south. Yeah. I am afraid I have to say I don't know. But, well, certainly, I don't know that much about the mountain permafrost, really, but at least in the Arctic tundra, human or traffic can easily cause thermocast. If you drive over the tundra on cars that compress the uppermost part, so that there is greater heat conductivity into the ground, then that can easily cause thermocast. So just to show you examples of thermocast, so this is very ice-rich permafrost that has collapsed here and here. This is a classic example of such disturbances on the tundra. If you disturb the layer of vegetation, plants and moss on the top, if you open up a rift in the top, then the permafrost melts very rapidly because it is just below zero. And these are just pictures that I took from a paper showing you thermocast. So I don't know if you can see the man standing here somewhere. When the ground collapses, this is what it looks like. This is in north of the tree line then, so that the water drains away and the overhang collapses because the ice-rich permafrost has melted and the water has gone somewhere else. And this is, I believe, from Russia, the collapsing permafrost by a lake. And, oh, well, I don't think you can see this. This is in Iceland, collapsing edge of a pulsar, a sinking pulsar in the central highland of Iceland. And because there is hardly any transfer of solid material when the pulsars arise, then all that remains when the frozen lens collapses is sometimes a little pond, or sometimes just like disturbed ground. So what happens when the permafrost thaws? Well, the active layer gets deeper, and if the summers are warmer and if the summers are also longer, then there will be more evaporation. And this might mean that the top of the soil no longer remains waterlogged, it actually gets dry. So the aerobic bacteria get really happy, and they start working and they start decomposing the peat and the plant remains. So instead of being a sink of carbon dioxide, the tundra may become a net source of carbon dioxide to the atmosphere. And it turns out, as I will show you in a minute, that the Arctic tundra, it stores huge amounts of organic carbon. And this is just a summary of what I have already said. There is ice underneath, so the meltwater cannot drain away. Evaporation is very slow, the soils remain waterlogged, aerobic bacteria cannot function. There's very slow breakdown of plant tissues. And if you compare the situation in the Arctic to the tropics, and it's completely different. In the humid tropics, decomposition is really fast. A leaf falls to the ground and it's decomposed almost immediately. and the plant roots take it up, and it's converted into plant tissues again. So at any one time, most of the nutrients in the ecosystem are in the plants themselves. It's bound in structural tissues, in the trees, in the woody parts. It's bound in the leaves and other parts of the plants. So what is actually sitting in the ground is very little. It's a tiny part of the total amount of nutrients in the ecosystems. But in the high north, in the Arctic tundra, this is completely opposite, so that at any one time, most of the nutrients in the system are sitting inert, underground, in half-decomposed plant remains that are of no use to the plants, because there is this bottleneck in the circulation of nutrients in the system. Plants take up nutrients, the leaves and the plant remains wither and die, but they rot so slowly. So the critical elements for plants, they're sitting in these half-dead, or in these dead, half-rotted plant remains, but they're not available for uptake. But this will change with global warming when the tundra becomes, when the uppermost layers become dry, and aerobic bacteria will become much more active and be active for a longer time of the year. So basically, one of two things could happen. It is so on this side of the picture, we have the anaerobic conditions. They may increase in some cases where you get thaw lakes, because what people have seen is that sometimes when the permafrost melts, you get an increase in lakes of very different sizes and different depths. And so these thaw lakes will actually increase the emission of methane from the tundra. The other possibility is that the tundra becomes drier, like I was talking about, and then the breakdown of the peat will be speeded up, and this will mostly emit carbon dioxide to the atmosphere. The latest estimates of how much carbon there is, how much organic carbon there is in the permafrost soils is actually rather disturbing, because it seems that there is twice as much in these permafrost soils as there is in the atmosphere, and it corresponds to about 50% of the estimated global below-ground organic carbon pool. So these soils, so it's 50% of the soils on, I think, about 16% of the land. So, what will happen? And where are these very thick peat soils and carbon deposits? So this is again a map. Blue are the soils that are estimated to have the least carbon, and then moving through yellow or pink really, and red. So you see that it is the lowland Arctic soils, especially of Siberia, that have these huge deposits, and in some places in Canada and Alaska as well. The mountain permafrost soils have much less carbon than the Arctic soils. Now, exactly what will happen is very, very complicated because there are a lot of other things that will change as well. Some of them may have positive feedback consequences and others negative. There have been more wildfires in the tundra, and that has an effect on albedo. It also removes the ground cover and the insulation so that may actually counteract the melting of the permafrost. The snow depth in the winter has an impact. The vegetation has a huge effect on the permafrost. The gradual movement of the boreal forest, the coniferous forest to the north, will have an impact. The increased shrub cover in the tundra will have an impact, and any changes in the moss and the litter layer will have an impact as well. Now, it is possible that greater plant growth in warmer summers and a longer growing season will counteract the increased emissions of CO2 by more photosynthesis and by more standing biomass, so the plants will fix more CO2 into plant tissues. Decreased summer moisture will also counteract it in some way by limiting heat conduction into the soil. So that the effect of global warming on permafrost and the consequences is actually very complicated, and it's very uncertain exactly what will happen, although it seems that most people agree that the counteracting effects will be much, much weaker than the direct effects, the forcing effect of the climate. So that a warming Arctic will lead to a warming permafrost. It will thaw. You can have either expanding wetlands with lakes forming in the tundra. From the lakes, there will be increased emission of methane, but also of CO2. If the lakes drain and if the top of the soil dries, that will lead to increased microbial activity and increased emissions of CO2. This is much more important than the emission from the lakes. I have no idea what the overall, how the equation is going to end finally, but as you can see then, yes, this refers to increased runoff, which may slow the conveyor belt in the northern hemisphere. On the other hand, so this is the sort of the negative side, if you like. On the other hand, the increased microbial activity will also make nitrogen more available, which may lead to increased plant growth and therefore to increased fixing of CO2. But unfortunately, this is likely to be of orders of magnitude smaller than the other side of the diagram. The timescales. Well, at least by the end of this century, the projections are that a great deal of the Arctic tundra will be permafrost-free, at least all the south part. So we are not talking about long timescales. There are enormous positive feedback loops in this, so that it is likely that it will, once started, it will escalate. We'll have. Yeah. Yes, well, everything in the Arctic has a seasonal timescale. So, this is, well, most of what I show here is what happens during the growing season. However, the microbial activity can proceed even at temperatures below freezing, below zero. So there will be some, it is expected that there will be increased microbial breakdown also during the winter outside of the growing season of plants. Yeah. Yes, like if you construct houses in like northern Alaska, you have to, if you want to heat them and you don't want them to sink into the ground, you have to, what they do is they raise them above the ground, and for example, and you have to put, they are on stilts or columns that are constructed so that the heat from the house is not transmitted into the ground. And when the Trans-Alaskan pipeline was built in the 1970s, I think, from the Arctic Ocean down to Fairbanks in Alaska and all the way down to the coast, then this is raised from the ground in all places. And I think they use sort of liquid nitrogen or something to cool, so that the heat from the oil would not penetrate into the ground. But if you see pictures of old houses in Siberia, you know, they're all sort of leaning or collapsed because they will gradually melt the top of the permafrost. Sorry, what happens to it? In sorry. Well, the permafrost may maintain what is called a false groundwater table. So the groundwater table itself may be quite low down sometimes, but because the water cannot drain from the permafrost, you may get a false groundwater table that is quite high, that melts in the summer, and yes, you could use that water, I suppose, but it's strictly not groundwater. I'm not sure if that answered your question. Well, thank you. Well, I don't really, unfortunately, I don't know that much about the permafrost in the high mountains, in the Himalayas. But I know that the melting of permafrost may affect landscape stability, so that you will have more scree slopes becoming unstable with the melting. And I also saw that the depth of the active layer is in those areas a very good indicator of soil moisture, so that, as you would then expect, as the active layer got deeper, the top of the soil would get drier. Well, I think Helgi would be a better person to answer this than me, but in most cases, most people do not define permafrost under glaciers or ice sheets. So they only define it outside the glaciers. Is that an answer?
Hello?